Hi everyone, this is your lesson 4 video on underestimate versus overestimate. Your learning objective for today is approximate a value on a curve using the equation of a tangent line. So this is actually the exact same thing we did in lesson 3. We're just going to add on to it a little bit. I want to do a quick review of linear approximation then, because that is what we're going to be talking a lot about. We've got f of x is equal to x squared. So if you remember back in lesson 3, we found the value of f of 2.1. We multiplied it out, we got 4.41. This was the actual value that we found. Then we decided to use the tangent line to get an approximation. So from the tangent line, we found that f of 2.1 was approximately equal to 4.4. If we take a look at those two values, they are definitely close, right? The actual 4.41, the approximation just straight up 4.4. 4.4 is a little bit less than 4.41, right? Think about $4.40 versus $4.41. So this was an underestimate, right? We used our tangent line, we found an approximation, and it was an underestimate. We want to be able to figure out whether something is an over or underestimate without having to calculate the actual value every single time, because that's going to get annoying real fast. So what I want to point out to you is we know what the graph of x squared looks like. We know it's a parabola that's got a vertex at 0, 0, and it looks like this. If I were to draw in a tangent line, right, at x equals 2, we're going to say that it's right there, we can see that that tangent line, that pink line, is underneath our function the whole time, except for where it's actually equal to the function, right, at that point of tangency. Everywhere else, though, that tangent line is underneath our function, which means any approximation that we do with a tangent line is going to be an underestimate. We want to be able to figure this out for every type of function, even if we don't know what the graph looks like. And that's where this idea of concavity comes in. So concavity is the curvature of a function. And it can be determined by examining the second derivative. If the second derivative is positive, it means that the function is concave up at that x value. And the memory cue for concave up that we're going to use, it's going to look like a cup. Concave up looks like a cup. So let's take a look where this would then be on our graph. So concave up, we're looking for a cup. That means it's going to be from pi to 2 pi. What that means then, I've got this graph of f of x. If I find f double prime, so in other words, the second derivative, and I evaluate it somewhere between pi and 2 pi, I should get a positive number. If the second derivative is negative, then the function is concave down at that x value. Concave down is going to look like a frown. So concave down, if we look at our graph here, that's going to be from 0 to pi. That looks like a frown, right? What that means then is if we were to find the second derivative and evaluate it, then we would have a negative value. So let's take a look at an example here. Find the second derivative of the following functions. Determine whether the graph is concave up or concave down at the given x value. In order to do this, we have to find the first derivative first. So g prime of x is going to equal cosine of x. Then we need to find our second derivative. So we're going to do g prime, or g double prime, of x. The derivative of cosine is going to be negative sine of x. Now I'm going to actually evaluate at pi over 2. So g double prime of pi over 2 means plug pi over 2 into my second derivative. So I'm going to do negative sine of pi over 2. I need to think about my unit circle. Pi over 2 is right here, right? It's the same as 90 degrees. That's the 0.01, which means my sign is 1, but I've got a negative in front. So -1 is going to be my second derivative. Well, what that means then is g prime of x is concave down at x equals pi over 2 because, and we do have to justify things here, because g double prime of pi over 2 equals -1, which is less than 0. If you want to just put g double prime is less than 0, that's totally fine. Since we know the value, it's probably a good idea to go ahead and put it also. But the main thing here is we know that it is concave down because the derivative, the second derivative, evaluated at that value is less than 0. Those are really the key pieces that we're looking for there. It's concave down at that point because the second derivative evaluated at that point is negative. So it would be concave down. In fact, if we look back up here, this graph, this f of x that's shown here, is actually the sine of x. And so if we evaluate at pi over 2, which is right here, we can see that along that function, at that point, the function is concave down. So it would make sense for it to have a negative derivative. So those two things kind of match, just to kind of show you what that looks like. We can determine whether our linear approximation will be an over or underestimate by looking at the concavity of the function. So what we just did at the beginning of the video was just talking about what does concavity even mean. Now we're going to talk about how do we actually use it. So if a function is concave up, then we know it looks like a cup. If I've got a function that is concave up and I draw in a tangent line, so let's say I've got a tangent line maybe right here. That was a really bad tangent line. Sorry, my computer. There we go. I've got a tangent line there. I could also draw a tangent line over here, right? Really anywhere along this whole interval that I drew, my tangent line is below my function. So tangent line is below the function values. If your tangent line is below your function value, then you're going to have an underestimate. And it's going to be an underestimate because f double prime of the number, whatever number it is we're evaluating, is greater than 0. So we're going to be justifying our answers a lot moving forward. That means you're going to want to have this justification written down. So if the function is concave up, it's going to be an underestimate because concave up means the second derivative is positive. If a function is concave down, it looks like a frown. If you draw a tangent line on a function that's concave down, that tangent line is going to be above the function. So tangent line is above the function. Well, if we're above our function value, then it means we're going to have an overestimate. And this is going to be an overestimate because the second derivative, evaluated at whatever number we're evaluating it at, is less than 0. That less than symbol is really high. Sorry about that. Less than 0. So let's take a look at what something might look like for an FRQ. The table below gives values of f and its derivative f prime. The second derivative, f double prime, is greater than 0 on the interval from -1.5 to +1.5. Is the estimate for f of 1.2 obtained by using the equation of the tangent line at x equals 1, an overestimate or an underestimate? Justify your answer. This problem should look familiar. We actually estimated f of 1.2 in lesson 3. This was part of your lesson 3 warm-up. So we're going to figure out right now, is that estimate that we found an over or underestimate? The thing I want to highlight here then, we're just asking, is the estimate an over or underestimate? We don't have to find it because we already found it the other day. In order to decide if this is an over or underestimate, we need to think about the second derivative. So think about f double prime of x. Well, something really important here in all those words that I read at the beginning, it said f double prime of x is greater than 0 on this interval. 1.2 is inside that interval. It means then, if I read that carefully, it means f double prime of 1.2 is greater than 0. If the second derivative is greater than 0, the function is concave up. If it's concave up, we know that the function looks like a cup. Our tangent line that we draw then is going to be below our function, which means this is going to be an underestimate. So we're going to write it would be an underestimate because f double prime of 1.2 is greater than 0. Make sure when you write this that it's f double prime of the number that we're actually looking at. All right, it's not f double prime of x anymore. We're looking at a very specific value. So that's something I want to make sure you make a note of. All right, we will do the other problem as part of your warm-up. So if you have any questions, please make sure that you wrote them down. We will go over any and all questions when I see you back in class. Thanks so much for watching.